That's actually also going to be the title of the future James Bond movie. Shaken, not stirred. Okay. Substitution reaction. Okay, how do we do on, not that one, that's not it. Over here, next page. How do we do on this here? Somebody have product here? This is an ether, yeah? An ether. Right with HBr, can we get a product? What do we propose here? Anybody have products? More generally, the oxygen becomes the leaving group. That may come from the fact that we're under F2. Really? No. 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 I'm predicting yes. No. Yes. No. 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 Okay. What? Okay, here we go. We got to start thinking broader here. Okay, what chemistry can we do here? What can we do? First step. We're not just going to magically fill up a product and say there's the. We're going to think through it. What can we do first? Do we have any reactivity here? Protonate oxygen. Yes, we've done that a couple of times. You can always do that. This is a strong acid, H plus Br minus. Yeah, and we can get to this here. That makes oxygen a better leaving group, yeah? We can do leaving group chemistry. Okay, so what do you want to propose next? Br minus. Where's the Br minus going to attack? Br minus will now attack where? Right here. And kick off the leaving group. Yeah? We'll kick it off. Leaving group gets kicked off by what type of mechanism? SN2. I just did a concerted. I didn't make a carbocation here. I added in backside of the transition state here and kicked it off. Now what does that give? Gives that. Plus what? Plus that. The bromine is now on that carbon, and that's an ethyl there. Yeah? Substitution. This was the leaving group. You see right there it left that carbon. Why did you guys attack here and kick the oxygen off of there? Before you answer, let me remind you of the first line in this handout. The title of this handout is Nucleophilic Substitution at what type of carbon? Yes, tetrahedral carbon. That's not a tetrahedral carbon. Okay, if we want to draw these pi bonds in very precisely, right? That carbon is sp2 trigonoplanar. Basically, you have two choices here. If this was an alcohol, this would be another H, and that's the only carbon to attack. We have choice here. We're not going to attack there. not a tetrahedral carbon. You don't do SN1 or SN2 on a non-tetrahedral carbon. Only tetrahedral carbons do you do these mechanisms on. Okay? Now, a day or two ago, I said tetrahedral carbon about 20 times because I knew that this point was coming. But all right, it's also there. Why do you not attack it here? A couple of reasons. First off, if we add it here, which bond is going to break? The sigma bond or the pi bond? The weaker pi bond would break before the sigma bond did. And so this would break this way or something. And that's a different mechanism. And we're not doing that in this class. But you would have a stronger bond. There's other reasons you don't do it. I don't want to take the time to go into it. Everybody trust me, you don't do SN1 or SN2 unless it's tetrahedral. Yep? The only tetrahedral carbon you have here, not that one, you attack here, kick it off, they're your products. Yeah? Good? Okay. Otherwise, is it straightforward? We protonated the oxygen, made a better leaving group. Can Br minus act as a nucleophile? Yeah, at this point, anything with a lone pair can act as a nucleophile. We'll talk about nucleophilic strength. In the lab you're doing this week, Cl minus is acting as a nucleophile, right? That reaction probably requires some heat. So if you actually did this, you probably might be heating this. What do we do? We don't even need to really talk about it. See if you can answer this. The ether was converted to what? Well, you might say which one? The alcohol. I mean, ether cleavage to give alcohol, so it's a common reaction. Do you need to memorize that? No. I mean, it's an alcohol. It's actually a phenol. Depends on which one you're sort of focusing on. It gives two organic products. Okay, what do we need to remember? Well, I've already stated it a couple of times. Can you remember that? Tetrahedral carbon. Okay, good. We need to talk about this protonation of oxygen. How much is this favored? I mean, is this a good base? Is oxygen a good base? We can just draw that phenol. You already got it there. I just erased it. How good of a base is that oxygen? Go back to acid-base chemistry. Did we consider that neutral oxygen a good base? No, we only consider neutral nitrogens, sp3, maybe sp2. Yeah. So why are we able to do this? No, there's no resonance. You're saying there's resonance here? I mean, if we draw this out, there's no resonance here. Make sure you understand that. There's no resonance that involves delocalization of the cation. There's no resonance stabilization of this cation. Why are we able to do this? Well, I mean, it's got a lone pair. That doesn't mean the equilibrium is good. The equilibrium looks like this. Okay? It's a very poor acid-base equilibrium. That doesn't mean we can't have maybe one, and then you have a gazillion of these, 10 to the 15. A gazillion in one of these. But guess what? Then this one reacts, and it moves on to products. And when this reacts, what happens to this equilibrium? It adjusts. And if you remove this from the equilibrium, how does this adjust? Le Chatelet would be wanting to hear the answer. If you remove one side from the equilibrium, how does the equilibrium adjust? It shifts to create more of that one. So when this is removed, what happens to this? More of this is converted here. One more, and then it reacts, and then one more, and it reacts, and then one more, and it reacts, and it keeps. And before long, the whole thing is moved this way through the equilibrium, even though the equilibrium is very bad. Because in the reaction, this is removed from the equilibrium as it continues on. Okay? Oxygen's a lousy base. In practice, you're never going to protonate that oxygen and isolate this. This one, you can never isolate this. It'll just fall apart. But in a mechanism, it can be a intermediate that is just a transient intermediate. Okay, B. How else can we convert an OH to a good leaving group? We can convert it to a tosylate. Tosylate is the main one you're going to see in your textbook. More advanced level, you'll also see mesylates and triflates. They're very similar, just a little advanced. Tosylate's the most common. Introductory. Tosylate is abbreviated OTOS. That's my abbreviation. Strictly, it's OTS. I like to say OTOS, though, so I put the O in there. Okay, what is tosylate? The oxygen is bonded to the SO2, which typically is called a sulfone. And then the sulfone here is bonded to benzene with a methyl. You don't know that yet. You'll learn aromatics in organic 2. Benzene with a methyl. Anybody know it? They sell it at Home Depot in the paint section. They probably sell it at Sherwin-Williams. Maybe, maybe not. I think they sell it at toluene. Toluene, used as a paint thinner sometimes, maybe not. Naphtha, maybe. Probably toluene is in naphtha, naphthalene or naphtha. Toluene, toluene sulfonyl. Toluene sulfonyl is shortened to tosyl. Toluene sulfonyl. And with the oxygen, it becomes the 8. So that's where the name comes from. Toluene sulfonylate. That's kind of long, so we'll just say tosylate. Okay. And the tosylate is a good leaving group. The OTOS, which is the tosylate, the O. Why is it a good leaving group? Basically, nucleophile, come in here, kick that oxygen off. You do not have to protonate the oxygen here. You do in everything above, but not here. Because that's going to give what? We'll have the nucleophile now bonded to the tetrahedral carbon. What did we kick off? O, S. Instead of drawing out this big group over here, this group can be a toluene. It can also be just a methyl. And if it's just a methyl, it's called mesylate, methyl sulfonylate. Yeah? Sound reasonable? Mesylate. This one's very good. This is the most common on the advanced level because it's most reactive. The best leaving group. Trifluoromethyl sulfonate. It's called a triflate. But you may not see triflate in your textbook. Tosylate's the most common. Can I just say R over here? Generic for some type of carbon group over there. Okay, when that leaves, what's the charge of the oxygen? Minus, right? There's 2 lone pairs here when that leaves. Good leaving group. Why is it such a good leaving group? Any argument we can make? The fact that it leaves implies that it's stable. Why? Yes, it is resonance stabilized. We can do resonance, electrons in, move these up. Yeah? And we can start drawing resonance structures. This oxygen is delocalized onto that oxygen and also onto this oxygen. It's a very delocalized anion and thus very stable. It looks a lot like sulfate. That's minus. If we put another OH over here or something, I mean, we can make that a -2. It's a lot like sulfate, which is very common, very stable. Sulfuric acid just converts to sulfate whenever it can. Tosylate, the oxygen does not need to be protonated to leave. So in that regard, it's a lot like a halogen. You don't have to protonate a halogen to make a good leaving group. It's already good to go. Because it's kind of like a halogen, it's sometimes called a pseudohalogen. All right? You need to know the structure of tosylate. Now, while we're here, I could point out a couple of these here. If that was an H and if that was an H, what would this molecule be if those were H's? Sulfuric acid, yes. That is the dimethyl ester. You can have sulfate esters as well. The dimethyl ester of sulfuric acid. Sulfuric acid is very cheap. The dimethyl ester is also very cheap. So is the diethyl ester over there. Those are very cheap. You can buy a jug of them for very low cost. So they're very common. But here, now it's not, you don't have a methyl tosylate here. Okay, methyl, this is not a toluene over here or any of these. It's got a repeat over here. But it still acts the same way, and we can attack the carbon and kick that off. Just like we did here. So again, it's not a tosylate or mesylate, it's actually the dimethyl ester of sulfuric acid. I point these out because they're just very common. But the chemistry is analogous to like a tosylate. Now you might think, could it also attack over here? Usually these only serve as one. What is this providing? It's a source of what? What is this a source of? Let's talk about that terminology. You have a nucleophile and you bring this in. What are you really bringing in that you want to add to your nucleophile or react to the nucleophile? What ends up bonding to the nucleophile as a result of this coming in? Right there, right? That's now bonding to the nucleophile. What type of group did I circle? Day one, we called that what type of group? Alkyl group. Yes. The nucleophile is being alkylated. I agree with that term? If the nucleophile reacts and you put a methyl on your nucleophile by this SN2 reaction, you're alkylating your nucleophile. It's a template term. It's a basic term, but you need to know that. You ever heard of alkylation of DNA? What does that lead to? Methyl is an exact type of alkyl. Propyl, they're all alkyls. Butyl, octyl, those are all alkyls. Methylation of DNA does what? It has to do with epigenetics and expression. Yeah, epigenetics, or it could lead to cancer. Or in some cases, it may be a good methylation. Not all methylations are bad, but alkylation of DNA typically is bad. I mean, but what does alkyl mean? Methyl, ethyl, propyl. What's the most common? These tend to be very reactive. A tosylate, in terms of halogen, it's like an iodide. I mean, it's a great leaving group. Just like iodine is your best leaving group of the halogens. Tend to be very reactive, very eager to leave. These things are potent alkylating agents. They're so reactive. Terminology. All right? Potent alkylating agents. Do those sound toxic? Yes. Toxic. This one's particularly toxic. Why is it more toxic than that one? And that one's still toxic too. What's the difference? And what's more toxic? I mean, more reactive. Why is this more reactive than that? Which reaction is going to be fastest? Why the first one?
There's only one carbon with less branching.
Yes, there's no carbon here. We're adding a carbon. That's like substitution. right? Did we cover that?
Yeah.
Yes, right here. I mean, instead of a tosylate or whatever, we got a bromine here. That's more reactive than this. That's more reactive, okay? It's all there. Okay, let's look at how do you make tosylates? Usually you're going to have to make them. You can buy a lot of halogenated compounds. You don't often buy too many tosylates. Usually you have to make them. Tosylates are made from the alcohol, and you use tosyl chloride. Tosyl chloride is with chlorine there. It's a type of R group. And if the R group is the toluene, that would be tosyl chloride. And pyridine. Pyridine is a weak base. It's benzene, but with a nitrogen. sp2 lone pair. It's a weak base. Okay. I'm not going to show mechanism here because it's a pi bonded atom with a leaving group. The oxygen is going to be bonded to the sulfur. That's what you see here. Oxygen is bonded to the sulfur, right? See it? And then what's eliminated here if these react to make that plus what? HCl? Yeah. The pyridine picks up the HCl as a weak base. It also helps sort of maybe catalyze the reaction. In organic 2, we'll look at this mechanism. It's a substitution reaction. The oxygen replaces the chlorine, but it ain't SN1 or SN2. We get the tosylate. And of course, when we make the tosylate, if we have stereochemistry at this carbon, there's no change in stereochemistry, is there? We didn't do any chemistry here when we made the tosylate. So there's no change in stereochemistry. But now we can come in with some type of nucleophile. We got this pseudo-halogen. It's good to go. And we can come in here and kick it off. SN2, right? Concerted backside attack. And now we get inversion, right? Because just like Big Mac comes with fries, what does SN2 come with? Inversion. All right? SN2 comes with inversion. So, stereochemistry, yeah? And ultimately, what did we just do in that section? We made the OH a better leaving group, not by protonating it, but by converting it to a tosylate. And when you do this, that's a separate reaction here. Usually you're going to isolate the tosylate, purify it, isolate, and then you do a separate reaction. Where the protonation is a step in a mechanism. You're never going to isolate the protonated oxygen like we discussed. You're never going to isolate something that's only one out of a gazillion. Okay, 3. Well, what was 1 and 2? I think 1 was halogens and 2 was oxygen. Halogen, oxygen. What else can we talk about being a leaving group? What about nitrogen? Can it be a leaving group? Yes, but as with oxygen, only if it's given a positive charge. Nitrogen will not leave unless you give it a positive charge, like oxygen. Also, nitrogen being a leaving group is kind of less common. Oxygen is pretty common. Nitrogen, we're getting into sort of uncommon territory. But it still can happen. Here's a reaction. The Herzog-Meyer reaction, which is the dealkylation. What does dealkylation mean? Removing an alkyl group. Okay. Dealkylation of tertiary amines. Is that a tertiary amine? Yes. with HI. If you react this with HI, we can get this compound and methylidate. Can you show mechanism here? Okay. What do you want to do first? Protonate the nitrogen? We can do that. Nitrogen's not that basic, is it? Why is it not that basic? Lone pairs in a p orbital, and we have always said lone pair in a p orbital is not basic. Neither is an oxygen. But we protonated oxygen. Again, like I'm telling you, there's a difference between something being a base and being able to protonate it. For me, when I call something a base, that means when I go to the lab and attempt an acid-base reaction, it's going to do something. And maybe I can make a salt, okay? You can protonate anything in a lone pair, but that doesn't mean it's going to be practically good in doing acid-base chemistry. But again, in a mechanism, it doesn't matter that it's practically good. All you need is 1 out of a gazillion. Okay? Terrible, it's a very weak base. It's actually a little bit better than we're saying. But again, it's a lone pair. We can do this, yes. Okay. What do you want to do now? Okay. Maybe we should draw this as a CH3. I don't know. I don't like to use condensed stuff. And ME is really hardly not even condensed. It's an abbreviation. Ultimately, what's going on here, though, the iodine then attacks the tetrahedral carbon and kicks off the leaving group. And what is that right there? First off, what type of mechanism am I doing? It's an SN2. What does this give? It gives that. Again, that was the leaving group. It all depends on probably what you're after here is that. And so you may not want to just put the leaving group in the waste container. You maybe want that's your main product. We also made methylidide. I mean, the substitution was done on that carbon. Actually, that carbon, right? I'm just sort of showing the leaving group as the main thing, and in the reaction, dealkylate. What did we do to this? To this. It's now this. That's still it. It's like a car. If you remove the one tire from a car, it's still a car. It's just missing a tire, right? You don't call it something else, or like no longer consider it a car if you remove the tire. We just removed the methyl. This is still it. But we've removed the methyl, which is an alkyl group. We've dealkylated a tertiary amine to a secondary amine. That's what we did in this reaction. That's called a Herzig-Meyer reaction. Now, some of you are old enough to remember, but Herzig-Meyer, they used to sell furniture over on Wrightsville Road. Anybody remember that? You do? Okay. Okay. I should just It was called Hurley-Meyer. Not Herzig. But Herzig-Meyer is the name of that reaction. That's a bit, you'll never hear that. Please, you don't need to know that name. Most of the time when we hear a name reaction, it's very important. Every other time, that one, no. There's probably nobody else in the state of Georgia showing this reaction in organic chemistry. I do because it's an illustration of nitrogen being a leaving group. It's common, okay? Diels-Alder, on the other hand, you need to know Diels-Alder. Williamson ether synthesis, need to know it. Okay? Wittig reaction, need to know it. Herzig-Meyer's, not so much. But you do need to know the chemistry there. Not the name. Okay, what other atoms could be leaving groups? What about sulfur? Can sulfur be a leaving group? Yes, but just like oxygen and nitrogen, typically only if it's made positive. Okay, and actually your body uses sulfur as a leaving group a good bit. The body also actually uses sulfur as a nucleophile a good bit. When your body makes epinephrine from norepinephrine, how does it do that? Norepinephrine, what's the difference between the two first? Methyl group on nitrogen, yes. Epinephrine. By the way, what's another name for epinephrine? In England, Europe, they call epinephrine what? Adrenaline, yes. Noradrenaline. By the way, what does nor mean? Nor is often seen in organic nomenclature. Nor means something that's been removed. Epinephrine. Norepinephrine sounds like something's been removed from epinephrine. What's been removed? The methyl group, yes. Okay, when something's been removed, a lot of times you just put nor in the front of the name to indicate something's been removed. But going this way, we're adding the methyl. Okay, how do we do that? Your body has this sort of enzyme or coenzyme called SAM. You can actually buy it at in the drugstore, Whole Foods or somewhere. Take it as a supplement. Okay, it's got a sulfur here with 3 bonds, positive charge. One's a methyl, nitrogen here, good nucleophile, attacks the methyl and kicks off the positive sulfur in an SN2 reaction. But that doesn't give the product directly. What does that give? I'm just going to call that mostly R, and we have NH2 now bonded to what? CH3, but this is now a positive charge. We didn't magically lose H's. But now something has to take the H and go neutral. Because here we're using a neutral nucleophile that becomes positive in the SN2. What can take the H? There's got to be a minus here. I'm showing a plus. There's got to be minuses here. Or what could take it? Water. Okay. All right. Make sure you always hydrate, drink water, so it can do mechanisms. Okay? Water or something to take the H, right? One of the H's, take the H, leaves electrons behind. And so maybe we produce H3O plus or something, you know, a variety of things in the body that could take, you know, the pH of the body. There's acids and bases all around depending on where you're at. Okay, that's a reaction in the body. Your body uses that sort of coenzyme. If you think you need more methylation, then you can take a supplement. All right. I don't know what what the proposed enhancement of that is. Maybe you want to make more epinephrine in your body. But it's interesting that that is sold as a supplement. You can actually find it, SAM, on the supplement aisle. It's actually a methylating reagent. I wonder why it's not toxic. I mean, your body uses it. Application of sulfur and nitrogen leading groups. You ever heard of mustard agent? Mustard gas? Things like that? Bad stuff. Used in World War I. Sulfur mustard. This was used in World War I as a war gas. Very, very bad. And held this stuff in for the eye blinding and bad stuff. Why is it so bad? Because it's so reactive. Why is it so reactive? Well, it's reactive in sort of an SN2 to nucleophiles. Nucleophiles in your eyes. Okay? It's a unique first activation step. You've got an internal. This is a lone pair. Show it down here. Show it here. This can just come in here and kick off the leading group. That's an internal sort of reaction. And internal reaction is very easy because they're right there next to each other. All right? And this is splitting from one molecule into two. Call that a molecule, or it's splitting apart, driven by entropy. But now look at it. This, which is driven by entropy, led to this three-membered ring with a positive sulfur. That's actually very good. Sulfur's positive. It's now a good leading group. But also because of the ring strain, that thing is dying for something to come in there and open it up. Now some biomolecule comes in here. We attack the tetrahedral carbon and kick off the positive sulfur in an SN2 reaction. And now your biomolecule is bonded to this carbon. It's sometimes called a neighboring group effect. Okay? This effect leads to a very reactive intermediate. And you can't stop this from happening, especially once this gets into maybe an aqueous environment that's more polar. Because by doing this, it becomes polar ions, just like HCl. If you put it in water, what's it going to become? It's going to become H3O plus Cl minus, right? Why? Because it's a polar system. You can't stop that from happening, just like you can't stop this from happening if you put it in water. And so essentially this is this. Extremely reactive. By the way, this, after this bonds, the Cl can take the H. This is another reason it's so bad. It produces HCl. And so not only is it reacting with the proteins in your bodies or lungs, but it's also producing HCl. And that's just as bad too. Then the acid is going to cause all types of problems. It's just bad news all around. Okay? Sulfur mustard. They call it mustard because this compound is yellowish. A lot of sulfur compounds tend to be a little yellow. Now, this can actually be used for better reasons other than the war gas. Some cancer drugs operate in the same type of idea. Chlorandecyl is a nitrogen mustard alkylating reagent used to treat leukemia. Same type of thing. This reacts here, and you get a three-membered ring with nitrogen. Then your DNA or something will come in and react. Some biomolecule will react. Now, if this reacts indiscriminately, it's just going to cause bad news. The only way that such a drug would be good is if it only reacted with the cancer cells. And if you can get selectivity. You want the cancer cells to start alkylating and mess them up. So then they'll die. But you don't want your good cells to do that. Well, that's very difficult. And a lot of these drugs, older drugs like that, just don't have any good selectivity. And so they tend to be quite toxic to the patient. And really, it's like, can we kill the cancer cells before we kill you? Okay? But, you know, the rest of the molecule can maybe promote the selectivity, but that's a big area of research, how to get it selected for the cancer cells. We're down here, this is just going to be, there's apparently no selectivity there. So there are some cancer drugs. Most of them are old because they're just not that, you can't achieve the needed selectivity. You know, to a degree. But at some point, there were some of the few alternatives that were available for treating cancer. Okay, what did we look at there? That was G. F, I think, was leaving groups. Carbon, can carbon be a leaving group? Typically, carbon ain't going to be a leaving group. And hydrogen, not going to be a leaving group. We looked at the ones that are going to be leaving groups. All right? Mainly halogen. Tosylate is a pseudohalogen. Oxygen, if you can make it positive, pretty common. Nitrogen, sulfur, not that common, but we see that the body likes to use sulfur. Okay, G. Let's look at the nucleophile. Okay? That component of the reaction. Again, we're mainly focusing on SN2 right now, but the things we're saying could also apply to SN1. In terms of leaving groups, yeah, SN1. Nucleophile on SN2 rate. Well, that makes sense because the nucleophile is not involved in the SN1 rate determining step. So why would you look at the rate, the effect of the nucleophile on SN1? You wouldn't. So, I mean, only SN2 applies here, right? Okay, let's look at nucleophiles. Anions are more nucleophilic than the neutral. Hydroxide is more nucleophilic than water. Now, of course, a nucleophile is, in an SN2 is looking to attack the partial positive carbon, kick off the leaving group. Which one's going to be more attracted to the partial positive carbon, hydroxide or water? The anion. They're both oxygen. They both may lead to the same thing after this loses a proton, but this is going to be more reactive, more nucleophilic. Same thing over here. That's more reactive, nucleophilic than ammonia. The anion is more nucleophilic than the neutral. Yeah? SN2. All right. Second, a less electronegative atom has a more nucleophilic or reactive lone pair. Less electronegative. Now, a lot of these trends here are the same with our base strength. Which is a stronger nucleophile, ammonia or water? They're both neutral, so that's not the answer. We have a difference in electronegativity, nitrogen or oxygen. Which one's more nucleophilic? It's the same as which one's more basic. Ammonia, right? Why? Because the nitrogen doesn't hold the lone pair as tight. Nitrogen is less electronegative. The less electronegative atom has the more reactive or nucleophilic lone pair. Ammonia is more nucleophilic than water, even though both are neutral. I mean, they're both neutral. That's an example in the same row. What about same group? Which is more nucleophilic, H2S or water? Well, the answer is already given, H2S. Why? Well, sulfur is less electronegative. Oxygen is a better pair, and it holds the lone pair closer. sulfur lone pair is more out here able to react with the partial plus. Which is a better nucleophile, I minus or F minus? Well, the answer is already given. Why I minus? Less electronegative. The lone pair is out there more, able to interact with some type of orbital here or whatever bonding is going on. All right? Steric effects. Steric effects of what? We've already looked at steric effects of the electrophile, the thing with the leaving group, right? What about steric effects of the nucleophile? Well, sterics also negatively affect there. For example, a primary amine is going to be more nucleophilic than secondary, and that's going to be more nucleophilic than a tertiary amine. If we consider like a neutral amine series here. Why? Well, once you start getting these groups on here, it crowds around the lone pair, and it's not going to be able to get close to this carbon as much. Okay? I mean, it's just like me coming up the aisle here or whatever. If I come up to consider this a big wall, if I come up here like this, I can go right through. But if I come in here, consider this two walls. If I come in here like this, well, I'm going to start hitting everything, right? Or it's like an airplane trying to go into a narrow hangar. If it's got wings, it's just going to break them off. But a blimp or something can maybe go in there. All right? It's pretty straightforward. Sterics, either in the electrophile or nucleophile, hurts the reaction. It leads to crowding, and things can't come together as much. In fact, tertiary amines can be a pretty difficult substitution reaction. And actually, the tertiary amines, such as triethylamine, are often used as a non-nucleophilic base, such as for E2 reactions, which we'll see. Of course, it's a base, it's a nice, but it's considered non-nucleophilic because it's tertiary. And it doesn't like to act as a nucleophile, but it will act as a base. Because base reactions aren't inhibited by sterics. Why? Because the proton is so small. Right? We'll end here. What's the difference between a base and a nucleophile? Something's called a base when it attacks a proton. If it attacks anything else, it's called a nucleophile. Okay? If it attacks here, we call it a nucleophile. Okay? If it attacks an H, we call it a base. Most of the characteristics are the same. But actually, this is a good base, but allows a nucleophile. Because nucleophiles are affected by sterics. See some of you this afternoon. Upstairs. We'll get started at 2:30. We'll have a quiz soon, including mass